Hit record. There we go. We're started. Happy Garbage Day.
Happy Garbage Day.
Welcome one, welcome all. We have a formative assessment number 2 to be discussed, and Bladimir is going to lead that charge. Of course, he has some lovely materials prepared for you. So the HTML file is in the other tab here.
Yes.
And then I have your PowerPoint that you made as well.
Awesome.
And I'm going to sign in on my phone so I can run the Zoom waiting room for you.
Yeah, thank you, Lisa. Thank you. Let me press this. Great. Hi, people on Zoom. Hope you are doing well. Hi, people in the classroom. I hope you are doing well too. Today we will be discussing questions for formative assessment 2. I have a set of slides with some things that you could consider to understand what we were looking for. And we read your answers. Thank you so much for taking your time to give us your responses. So we will be trying to combine your discussion with some of the contents that we have covered in lecture 2A specifically, which is lecture 2A, right?
Lecture 2, example 2A is binary.
Lecture 2, example 2, thank you. Yes, I have that here, that reference here. Yes. So let's go to the questions first. I have the same question, so I will be using the slides. Awesome. Yep. Can you see it well? Okay, so let's go. Question 1. What problems would be created by predicting a binary or ordinal outcome using a standard linear model or a standard general linear model? What do you think? Yeah, I know that answers are there, but when you read this question, what was the first thing that you thought? What was your first impression or clue about problems in this case? I'm reading the chat too.
Yeah, I would say my biggest thought was continuous versus discrete variables.
Yes?
I mean, you cannot predict discrete with continuous very well.
Mm-hmm. Yes, I think that can be related to option 1 here, the mismatch between the outcome scale, something that has limits or something that's continuous, with respect to the linear predictor, with respect to the model. Now, something that we read in some answers was the idea of an incorrect or misspecification in the linear relationship between the predictors and the outcome. However, one of the model assumptions is that whatever you are defining for your predictors in terms of the relationship between the predictor and the outcome is correct from the beginning. That means we can use a quadratic effect for one of our predictors, for example. So we have a nonlinear relationship between the quadratic predictor and the outcome, but if the outcome is binary, we will have the same issue as what we have been discussing now. So the linear relationship between the predictors and the outcome is not the main issue, but the relationship between the outcome scale and the predictors that we are using, or the linear predictor, better said. So those are not the same thing. Now, other things that you thought or considered, because in terms of prediction, you are right. In binary, specifically for binary data, we have zeros and ones, and we know that predictions can go out of the boundaries if we are using a general linear model. What other things did you consider? I'm reading the chat if you want to participate too. What do you think about residuals?
So I wrestled with the second part.
Yes?
Because I have an idea in my head, but I'm not sure if my idea is right.
Yes?
So I think that linear regression assumes a normal distribution of residuals. And if you are predicting a binary variable, it's not going to produce a normal distribution of residuals. But I think what I'm wrestling with is like, how we change the I understand we're predicting the log of the odds for probability of one instead of the probability of one. So
Yes.
the range is different. But like, are we forcing the data to fit the model? Is that basically what we're doing by transforming the probability into the log odds? So that then the residuals of the model, or then the residuals will meet the assumptions of the model.
Okay, so question is related to residuals in our model. We know that in the general linear model, we assume or we are working with normally distributed residuals, which means that we have a continuous outcome in our data. In logistic binary regression, we don't have such thing. Why mainly? Why we cannot have a normally distributed residuals? What do you think?
And the variance, like you can calculate the variance if you know the mean. It's not two separate things.
Yes, we don't have a separated estimated variance component because in the Bernoulli distribution that we are using for our observed data, variance depends on the mean because we know that the mean of the distribution, which is pi, determines the variance given that the variance is 1 minus pi. So that's one of the things. However, I'm thinking about how to explain this because that's why I created the example. Let me try to answer your question, but how could I rephrase your question? That's the first point, I think. How could I rephrase your question?
I'm struggling to even put this into words. I
Yeah.
guess what I'm trying to figure out is, so in order to run linear regression, you have to have continuous data where the residuals are normally distributed. But if you are looking at binary outcomes, the data is not continuous and the residuals are not normally distributed. So we take the log of the odds of the probability of the outcome, and then it kind of makes the data fit what's needed for a linear regression model. So then we can use linear regression because we've kind of forced our data to meet the assumptions of the model.
Okay. Okay. Yes. I think that first let's finish point 2 because that's related to what you are asking here. But we should go point by point because first things first. We know that we are not transforming our dependent variable when we are using these models, right? We are using, if we have a binary of an ordinal outcome, we are using that variable in the analysis. The link function, what it's doing is transforming the conditional mean that's being predicted by the model, right? That's how what the link function is doing. So now we have two things: model scale and data scale. We know that residuals in binary data won't be normally distributed because we don't have something that's being estimated separately. We don't have a variance in our residuals that's being estimated. That depends on the mean of our variable now. Then, if we don't have normally distributed residuals, we are violating one of the assumptions of the general linear model. That, together with the problem of predictions, are consequences of trying to predict something binary with the general linear model. Okay? Do you agree? Does it make sense? More or less. Okay, Lisa, do you want to add something?
Yeah, so you're not fixing it so that you can use a standard linear regression.
Okay.
Because when you say standard linear regression, you're talking about two things at once. You're talking about a linear predictor, like what did the fixed effects build as a predicted outcome, and then what's in the model for the variance. And so you're saying the E follows a normal distribution. We're not saying that. We're building a scale that's continuous so that you can use the linear predictor part. So you can have a set of fixed effects and predictor variables that together create some kind of linear composite. But then it doesn't go out of bounds because logits don't have variance. But we don't really have logits in the data. We have a column of zeros and ones. So I wouldn't think about residuals anymore in the same way that we do for continuous data. We're just saying that the outcome is distributed vertically, which means there's no separate variance that's constant.
So there's no residuals for logits. There's residuals for our predicted outcomes in the data scale.
Yes.
But there literally are no more residuals in the logit scale because that's not possible.
Yeah, take the logit as a probability, which is not an individual specific value. It's a prediction based on the model.
Okay, which is like saying we can go backwards from logits to odds ratio, but we can't go back, but we can't go backwards all the way to probability for the slope.
That is true. Although I think that's a different question.
Yes, I would like to add that in logistic regression, that residual thing that we have, it's fixed depending on the link function we are using internally. So when we are using the logistic regression, we know that the variance is fixed at pi square over 3, which is approximately 3.29. That's what we have because we are using that link function. When we use probit, given that we are using the the cumulative normal distribution as a reference, the variance is fixed at 1. And that's what we have. So we don't have residuals as a parameter being estimated in the model, right? So now,
I have one question, and if I'm way off base, let me know, but I thought that when we are predicting, when we get our logits and so forth, that's also often iterative process versus the standard general linear model. That's just, there's no iteration, it's just a calculation, and this is your line, not I'm iterating to try to fix my line or improve my line. Now, like I said, I could be off or, okay.
yes, that's a more advanced topic because to me that depends on the estimation method. When we use ordinary least squares, we know that we use something like an analytical solution, so we can have our parameters from the data directly. When we use maximum likelihood, that's an iterative process.
Yeah, so LLS, like if you want the regression slope, it's x transpose x inverse x transpose y, the end.
Exactly.
There's nothing else you have to do.
Right.
But for this, like you're right in that you have to figure out what model parameters make the data the tallest. And it's some kind of search process that uses calculus to figure out how close you are to the top.
Yes, but that's related to the estimation method, right?
Yes.
So, to finish point 2 here, regarding the violation of model assumptions, we know that when we are working with binary data or with categorical data, outcomes specifically, we won't have normally distributed residuals. And that means that our variance won't be constant because we will be using another conditional distribution for our outcomes, Bernoulli or multinomial, as we will see later today. Now, I was thinking about how to explain this part, and I created this example that I can share later. Well, Lisa can share this example later. I can do it. Great.
I think it fits here.
Here? Here it is. Okay, yes, I did it. So, I was thinking about this problem. I was thinking about the linear relationship between the model, the outcome, the difference between logits and probits, and linear model. So what I did, given that I already talked about the project in which I worked 2 years ago trying to predict the probabilities of admission, I took that data and I fed different models to show you the differences between logistic, probit, and linear and general linear regression. So just a brief context here. We were working with almost 80,000 students who applied to a selective university, and we were trying to predict the probability of admission, which in our data was almost 78%, and those who were not admitted were almost 22%. Okay, so this was our dependent variable. Now, specifically for this example, I started with empty models. So here I wanted to show you, these are our models. Here we are using the linked logit, so this is the logistic regression. Here we are using probit, the probit regression. And finally, this is a linear model, the general linear model.
And this is in R, correct?
Yes.
Yes. Just so that way people are looking at it, they know which.
Yes, this is R and this is the HTML file. If you want the RMD file that I created, I can also share that file so you can see all the details, because some things were hidden because I didn't want to add all the things at the same time. Okay? So please pay attention to these differences. In terms of the logistic regression, this is our intercept. Well, this is the odds ratio.
Yeah, I don't know what it's printing.
I should show the logits, the result in logit scale. Sorry for that. But the point is, across our three different models, well, this intercept is correct because given that this is the linear model, this is using the original scale in your data. That means a proportion of ones. We know that we can take our model results and apply the inverse link functions, depending on the link function we are using, to go from model scale to data scale, okay? So if we do that from our logistic model results, we can see that the empty model is predicting that 1 would be something like 0.78, which is correct because we saw that the proportion of ones is almost 78. Look at the Provit model results. Same thing. However, the inverse link function needs integration. So for some complex models, this could be harder. Now, in terms of the linear model, you can see that the result is the same. But now, do you see this inverse identity link function? That thing, it doesn't exist because the link function is just the conditional mean of the outcome. So most of the time you can see that this is being multiplied by positive 1, but it is the same thing. So you can see that these three different models, even when they have different model scales, the data scale will be the same thing. Okay? Then I added only one predictor, which is math scores, to show you how the results were consistent. So again, even when we have different model scale, across models, we will have almost the same conclusion about what the predicted probability of admission is, specifically for someone with a math score equals 550. Okay? Then I wanted to break this to show you what's the problem with boundaries. So what I did, I tried to predict what's the probability for someone at the maximum score, 850 in our data. And this is interesting because look at these results. For the logit results, for the logistic model, the probability would be almost 94. For the Provit model, almost 95. However, for the linear model, that would be over 1. That's the issue when we are using these models. So if you are interested in analyzing some specific profiles, you should pay attention to this and cut, for example, cut that upper limit. But that's not correct because we know that we should be using another model to try to analyze what we have in our data. So we will share this. If you have questions, you can email me. Yes?
Yeah, thank you. This is a really helpful example. Can we say essentially that the three models will predict very similar slopes, but when it comes to, like, if you want to predict specific outcomes, you'll need to have a logistic model, because otherwise it will predict some of the same, right?
Logistic or Provit for this case. But just because this is a binary variable. So then we will see that, for example, with counts, we also need a link function. The main idea here is how to predict something continuous in the model scale that can be translated to something within the boundaries in the data scale. To me, that would be a good summary. So we will share this and you can email me or ask questions.
Yeah, one more question.
Yeah.
I have so many. If you go back to the example, so you showed us that when we have an empty model, all three models predict the same mean.
Yep.
So that's good to know. And then when we are predicting the slopes, all three models predict very similar slopes, not identical, but similar. But it's when it comes to predicting outcomes that are farther away from the mean, that's where we get bad estimates. if we have the wrong model.
Yep.
Is that correct? Like the mean will usually be predicted equally across all the slope. Maybe a little bit of error, but pretty close. But then when you try to predict a specific outcome that's far from the mean, that's when you really run into problems.
Yes, the question is about the slopes in the models. Unfortunately, I cannot show you the model scale slopes because these are the effect sizes. However, I think that the problem is not the slopes because the slopes are in the model scale too. So even if numbers are different, they are reflecting whatever the predicted or the expected change in y for one unit different in x is for the specific model scale that we have. Model scale which depends on the link function we are using. So even if the slopes are the same number, the scale of the models is different. In Probit, that's based on the on C-scores. In the logistics is based on logits. So if the slopes are different or the same number, it doesn't matter. That's not a problem by itself, I think, because that depends on the model scale. Is that clear?
You're saying we can't compare slopes across models?
That's a good question.
I would say that.
Yes.
you know,
The y is different, so they all get decimals.
Yes. However, we also know that, for example, risk ratios are interpreted in a similar way as odds ratios.
So they gave those to you for Probit?
Yes.
Oh, that's hilarious. Okay.
So these are not the same, but as far as I know, risk ratios or relative risk ratios,
It's computed the same way. It's a relabeling.
yeah.
They show up in counts too.
Yes, exactly, in count data.
I think you have a question for that.
Yes, Devin, please.
No, I had a misinterpretation, I think, about the comparison of slopes. So maybe this is a question more so for ordinary outcome. So we're comparing the models at that point. We're not comparing the slopes, correct?
Sorry?
When doing ordinary outcomes, we're comparing ordinal outcomes. We're comparing the model, right? If we're grouping cumulative outcomes,
Mm-hmm.
right? We're comparing the models, not the slopes, correct?
The submodels. Yes, exactly. When we have ordinal outcomes and we use the cumulative link function, what we are comparing, well, that depends if we are using the proportional odds assumption. In that case, the slope of a predictor will be the same across submodels, but that's something that we can test.
Today.
We can relax that assumption. But for now, we know that in the case of ordinal variables, using the cumulative link function, the slopes are constrained to be the same across submodels. Yes. So let's go to question 2. What do you say to reviewer 3 who insists that you need to fit a Probit regression instead of a logistic regression? I think that most of the answers were correct here. So, what do you think? What would you say? Like a short statement, what would you say?
Same thing, different scale.
Sorry?
Same thing, different scale.
Same thing, but different scale, exactly. Yes, and I think that that's a perfect summary because we know that with different model scales, the conclusions will be the same. So now, there are things that we can do. For example, we can justify our decision. There are some things that logistic regression has. For example, the odds ratios. That's a good way to analyze the effect size of the slopes. What other things would you say to justify your decision? Why would you use logistic regression instead of Probit regression?
With Probit, you can't get your odds, so then you can't interpret.
Sorry? Yes.
With Probit, you're not able to describe things in odds or chances of something happening.
Yes, that's one reason related to the first thing, to odds ratios. I think that odds ratios are easy to interpret and we can analyze them in a proper way. Now, what about Probit? What do you think is hard in terms of Probit?
Put your integral back up.
Yes, the integrals. that can be hard, especially when you have complex models. So the logistic inverse link function is easier to implement. So you can go from model scale to data scale in an easier way. So yes, finally, what you could do is just run the probit model and show the differences, but same conclusions under both models. Those are the things that we can do.
And that would be a footnote in your paper.
Yes. All complementary materials if you want an in-depth discussion. Question 3 says, in trying to predict a binary outcome, how do the outcome scales of logit, odds, and probability relate to each other? This was something complicated, I think, sometimes. So, thoughts or things that you answer. What do you think? What's the relationship between these three different scales? Do you need some help? Because I can ask you, what do we have in our model, for example? What's the thing that we are predicting in our logistic regression? The log of the odds of the probability of a 1. Correct. So now, that's in model scale. However, we know that we can use transformations of these numbers. So if we want to analyze the effect size of a predictor from logits, what do? We take the logit and take... No, that's for the intercept. For the slopes, what do we use to compare effect sizes? Odds ratios, right? What's the odds ratio? It's the exponent of the logit. And now, if we are working with the intercept specifically, we can go from odds to props. How can we do that? Using this function here, which is taking the exponent of the logit over 1 plus that exponent minus the logit now. So we can go from one to the other in that way. Yes, Mike?
Small question. On your bottom answer on the right-hand side for your fraction, should beta sub 0 through x sub 2 all be in parentheses?
Which one, sorry?
On the very bottom, the bottom
Yes.
fraction, should that, but should that be in parentheses?
Yeah, you mean this part?
No, the whole thing. After the minus sign, the
Yes.
whole thing.
Yes, because that would be applied to the whole thing. Yes.
Okay, I just want to make sure I was understanding correctly. Thank you.
Yep. So, questions? Questions about this? Something that you think is not clear yet? Relationship between logit, odds, and props. Do you feel confident? If that's the case, we can move on. Okay? Awesome. Finally, describe how a cumulative logit or probit link function works for ordinal outcomes.
Sorry, Bladimir, I have a question on the previous slide.
Yeah.
Go back, just to make sure that I know the range. So probability is going to be like a probability of a 1. It's
Yep.
going to be in a range between 0 and 1.
Yes.
The odds are going to be between 0 and positive infinity.
Exactly. Yes.
And then the logit is going to be negative infinity to positive infinity.
Exactly.
So for the odds in the middle, if it's between 0 and 1, that's equal to less than 0.5 probability or negative logit. And then if the odds are above 1, then that's going to be equal to probability above 0.5
Mhm.
and positive.
That sounds right to me. Yes.
Very good.
Yes. Yeah, we are talking about the limits in props, logits, and odds. So props 0 to 1, odds 0 to positive infinity, logits minus infinity to positive infinity. And about the relationship, we know that probabilities between 0 and 0.0 are equal to odds between 0 and 1, logits, negative logits, end. And we know that in the case, well, it's the opposite. For probabilities above 0.5. Yes,
And
Rebecca?
then the odds ratio are the odds of a 1 over an odds of 0. So they also are a range between 0 and 1, just like correlation.
Sorry?
What's the range for an odds ratio?
Oh, 0 to positive infinity.
Really?
Mm-hmm.
For odds ratios, yes.
So just like for odds.
I think so, yes. Yeah.
Then an odds ratio is the odds of a 1 divided by the odds of 0.
Yes, the odds is the probability of a 1 over 1 minus the probability of 1.
Would it be
That's the odds.
Would it be appropriate to interpret? Because when you look at the odds ratio, can we say is it appropriate to interpret the strength of the odds ratio based off of how far it is close to or past one? Right. Yeah.
So yeah, I think because that's how effect sizes are interpreted, right? And we can use them to compare the fixed effects between slopes, and we can see how strength the effect is, or what the magnitude of the effect is. I think that both things could be correct. So,
Sorry, keep asking questions.
yeah.
I'm trying to connect. So this is why, if I remember right, some people don't like odds ratios because they're not standardized. And I think this is what I was mixing up in my head. Because odds ratios can be an effect size, but usually effect size are standardized so that you can apply them across different units. The reason why people don't like odds ratios is because they're not standardized. So they're not between 1 and 0, they're between 0 and positive infinity. And so that means depending on what unit you're looking at, it's hard to compare odds ratios to each other.
Yep. Yes, odds ratios are not standardized in the sense that they are not between 0 and 1, and they don't use residuals components to be standardized. I think that's important too. They don't involve standard errors or anything. That's the case for other standardized metrics or effect sizes. But the thing is, when you have a logistic regression, I think that we can use the odds ratios for that model specifically. Even when we have other measures, for example, in a general linear model, in a multiple regression, even in that case, if you have something like a partial R or semi-partial R, I think that the comparison is tied to the model. I don't know if you can compare effect sizes across models, even if you are using a general linear model, because the reference for one of the components of the effect sizes are specific to the model or data you are using. Right?
Yeah, so it's, the odds ratio is still per unit. And so if you're talking about like math goes up by 1, here's the change in your odds, versus if I move from a 0 group to a 1 group, here's the change in your odds. A unit is not the same. So they're not standardized, you're right. They're still unstandardized, but they're supposed to be effect sizes. So there's a mismatch in terminology.
Yep. Yep. So they are not, odds ratios are not standardized, but they are helpful in their way. That's what I want to believe. So, question 4.1, it says, describe how a cumulative logit or probit link function works for ordinal outcomes. What do you think? How would you respond this? I'm reading the chat, paying attention to that too if you want to participate or just talk to us. What do you think? How the cumulative link function does what it does? To answer this, well, this is a hard one. To answer this, I think that it is good to go step by step again. So, for example, in the way that I read slides 30 to 34, I think that a good summary would be that first, the role of the link function stays the same. Even when we are using cumulative, adjacent logit, or baseline, its role is to transform the conditional mean that's being predicted by the model. For categorical outcomes, a substantial difference is that we need binary submodels to be predicted now. And then, specifically for the case of cumulative link functions, we will have our binary submodels and we will have lower versus higher categories. And we can predict both sides depending on what we have in our model. For example, threshold for lower categories versus intercepts for higher categories. So now I would like to hear you. What do you think about this? Any question, thing that you would like to discuss? Is the idea of binary submodels clear?
Well, I just will add to that, and if I'm incorrect in my thought, please let me know. But if you have, C categories, in there, then you will have C-1 models. Is that
Submodels,
accurate?
yes. Yes.
Okay.
Yes, the number of submodels depend on the number of categories in your outcome. It's always C-1. And then those binary submodels will be dividing the categories between lower and higher references. Okay? Then finally, we have how does a cumulative link function for ordinal outcomes differ from the link functions used for nominal outcomes? We have seen 3 link functions so far. For ordinal outcomes specifically. Cumulative, adjacent logit, and generalized or baseline, right? So, what do you think is the difference?
Well, my first reaction was like, this is the first one that introduces submodels.
The 3, yes, the 3 create submodels because even when you are using adjacent, for example, it's the same principle, C-1 submodels, but now the references for the binary submodels is different. We will be comparing, let's say, 0 versus 1, 1 versus 2, 2 versus 3, instead of 0 versus 1, 2, and 3, 0 and 1 versus 2 and 3, or 0, 1, and 2 versus 3. In the generalized, is similar because let's say that we are using 0 as a reference. Now we have 0 versus 1, 0 versus 2, 0 versus 3. In all of these submodels, we have binary references. So, yes, I think that's a summary. But now, something that you would like to hear again about differences or model characteristics.
Can you just maybe restate what is it, like the main point you want us to get from it? Like, what's the main point you want us to lead with around this question?
What's the difference?
What's the main point you want us to get from this slide?
Oh, yes. Yes, the takeaway thing is when you have categorical variables, ordinal or nominal, you will must make a decision about how to predict the binary submodels. If it is an ordinal variable, you can use cumulative, you can use adjacent, or you can use baseline. Yep. However, when we have a nominal outcome, we cannot use the cumulative link function. Why? Because we don't have order in our variable. But we can use the adjacent link function at the baseline link function because we can use different categories as reference for our binary submodels. So that's the takeaway. When you must make a decision, consider what you have as outcome and how can you create those submodels. And that's related to the interpretation of the model parameters later. Okay? The software will let you do it, I'm sure. If you have a nominal thing, you can feed a cumulative, you can use a cumulative link function. However, the results won't make sense because the order you are interpreting is not there. Okay? And that's all for this. Questions, thoughts, impressions, opinions. Are we okay?
Thank you.
That's it. Thank you so much for your time. Thank you, Lisa.
Yeah, that's a common thing. The software will let you do whatever you want. Whether it means anything is a whole separate question. Yeah, it will rarely stop you from doing something stupid. It should be. Yeah, I am so short. Hang on here. I'm going to get this thing back down. There we are. There. So yes, the take home. If you have ordinal, you can use any of them. If you have nominal, stick with baseline. That would be what I'd recommend. All right, thank you for putting that together, Bladimir. I will post these things. Yes. All right, I'll get rid of that then. So let's see, I read through your answers and he did as well this morning. Your grades have been updated. The next thing is homework, what are we on? 2? 2? Yes. Ordinal. due the Friday before spring break.
Hi,
So
Jay.
you got 10 days or so. Any questions on that yet? And the question is, how could you possibly think I've started on something that's not due for 10 days? That's fine.
Unless you're Mike.
Unless you're Mike. Well, some people like to do their stats homework first because it's a very well-defined task as opposed to something that's more amorphous, like writing a master's thesis or doing a lit review or something where
Much
it's
more
like,
fun than that.
yeah, so you may choose to do the thing that is easier to start with, even if it's not due first. Because I do that. I will prep your lectures and do things like that I know how to do before I write something that I'm not sure what I want to say. So I speak the same truth as you here. All right, any questions on that stuff that we were just talking about? Did you get all your questions answered? Maybe? For now? Okay. All right. So should we go back to talking about ordinal prediction?
Yes.
See it in action? All right, we have done the empty model several times. Do we need to do that again, or are we good? Okay, so the idea of an empty model is to make sure that you understand what your submodels are doing. So
And you
now,
know your reference.
and I know what, yeah, I know which way it's going,
Yeah,
essentially.
which is up.
If I'm predicting the probability of the higher category or the probability of the lower category, that's the question. So we did a proportional odds model in which each of the submodels get the same slopes but different intercepts. So to remind you what the story is here, in example 2b, this is page 2, we are predicting a 3-category outcome. How likely are you to apply to graduate school? No, maybe, or yes, essentially. So that's why I have it written more concretely as to what the submodels are predicting. You could also write it as the probability that apply is greater than 0. I see people write it that way, a little bit shorter, but this makes it explicit. And as we discussed last week, the intercept has 2 subscripts because we're differentiating which intercept we're talking about. Is it the one predicting the probability of a 1 or a 2, or the one predicting the 2? So that I am denoting that with the second one, where I have this is the 0 model and this is the 1 model based on what you're greater than. But beta 1 is the same here and here, so that is a constraint. That is a new term that you may not have heard. A model constraint is when you force something to be a certain way. So I'm forcing these 2 slopes to be estimated as the same number. I'm forcing these 2 and I'm forcing these 2. So we looked at some of this output. I think we went through Stata mostly last time, so we should stick with R. So I am using for this example a function called VGLM because it was the only one for ordinal data that I could find that would allow me to have intercepts and to have non-proportional odds to allow the slopes to differ. So this is going to be like a baseline against which we can test what happens. So first things first, then, the code, family equals cumulative. That means this is an ordinal model. So put that together in your head. Cumulative link function is for ordinal. The flavor we're doing it is logit link. I'm not sure if this package has probit link, but I'm assuming it probably does. Reverse equals true. Do you remember what that does?
Sum from here to the left.
Yeah, it gives you intercepts instead of thresholds. Do you remember the difference?
No.
Threshold is the
No.
inverse of the,
There.
sorry.
He-
The proportion or the
Go for it.
probability of 0.
That's right.
Intercept is the probability of 1.
Yeah, let me get the picture out that goes with this idea. So this is slide 32. From the perspective of like it being the point at which your answer choice shifts. Like this is the point at which you would transition from a 0 answer to a 1 answer on the underlying distribution. So that value, for instance, might be a probit of -2. If I do integration to figure out what is the area under the curve up to this point, that corresponds to a probability of 0.16. That's the probability of a 0. So these thresholds are reflecting the expected outcome for the lower category of each of the binary submodels because they're from this switchover perspective. By the way, I had a couple responses in terms of the underlying distribution here. We don't have this. This is an idea that motivates the scale of the model. So there's no way that we could test whether logit fits better than probit because we don't have a continuous variable that they're based on. We don't have that data. So there's no way we could know. So we can't really make an empirical argument as to which we might prefer. We could use AIC and BIC, but I'm guessing that they would be mostly agnostic for these things. So yes, thresholds give us the probability of the lower category instead of the upper category. And if I want to switch it, like if I want to turn this into an intercept, what do I do to it?
Change sign.
Flip the sign. Yep, because logits are symmetric. So if I know the logit of the lower category is -2, that means the logit of the upper category has to be +2. So you only need to know one or the other. So reverse equals true means give me intercepts. Parallel equals true means force all my slopes to be the same. Yep, parallel lines. So that's why in the output, there's only one slope listed because it's being constrained to be equal. So who's feeling brave? What's that number mean? Intercept 1. Conditional mean for the first submodel. Yeah, the logit that goes with greater than 0. Yep, the logit that goes with greater than 0. Yep. For somebody who's 0 on all the predictors. So the reference person, so to speak. Yep, so this is the logit of the probability of picking something greater than 0. So the first submodel is saying what separates no from something else. The hard no's from the soft no's and yeses. The second submodel then is separating the hard and soft no's from the yeses. 0, 1 versus 2. So -2.5 is the logit that corresponds to the probability of answering a 2 instead of a 0 or a 1, saying yes instead of no or maybe.
Can you quickly, I know this has something to do with like the subscripts 0, 1. I mean,
Yep.
but how did you get to the point where you interpret it? What did you take into consideration to be able to interpret it?
Okay. So the R is just ordering, like these numbers don't have any tie to the values in your data. This is the first one, this is the second one, this is the third one. But I know my data go from 0, 1, and 2. So this first submodel has to be 0 versus 1, 2 because that's first in terms of the ordering. The second submodel has to be 0, 1 versus 2. And if I had a 4-category outcome, then I would have a third intercept sitting here that would differentiate the next one from the remaining ones. Yep. So GPA, people with higher GPAs are more likely to want to go to grad school. Are they more likely to choose a 2, or are they more likely to choose a 1 or a 2?
Oh, no.
Yeah, it's both. This slope is doing both at the same time. So for every additional unit higher of your GPA, your logit of answering either 2 or the logit of answering 1 and 2 is higher by 0.6. So it's submodel agnostic. That's a testable constraint. People whose parents went to grad school are more likely to pick the higher category in each submodel. People who went to private school, a little bit higher, but not significantly so. Okay, any of that you want to hear again? Zoomers, we hanging in there? They're quiet today. Okay, so we got the slopes. Now the rest of the output here. Residual deviance. This is how short your data are. This is -2 log likelihood where smaller is better. So we would watch this go down, and we would watch log likelihood go up. They're inversely related because this is -2 times log likelihood. VGLM automatically gives you effect sizes. So exponentiated coefficients, this is e to the logit slope. I looked this up the other day to make sure I could say it correctly. It is the number to which you have to raise the constant e to get that number back. Close enough? Yeah, so
Yes.
e is a number, like 2.71 or something like that.
Close enough.
So it's the number you have to raise that to get the original value back. And if you're like, what did she just say? This is the unlogited version down into odds. So these are all positive odds ratios. Does that mean that all of my slopes are positive?
No.
No, odds ratios can't be negative. Don't let this screw you up. Now they're all above 1. That tells me that these are positive logit slopes. 1 is neutral. 1 corresponds in odds to a probability of 0.5 to a logit of 0. So these are effect sizes, but for the reasons discussed earlier, they're kind of not. So the odds ratios, or the logit slopes for that matter, for grad versus private are comparable. These are both binary predictors where you can be in one group or the other. So you could think of this as like, which is the bigger benefit factor? Having parents that are highly educated or having a private school education? Which gives you the bigger boost? I could compare these two numbers. That would be a GLHT hypothesis test where I subtract one from the other. I can express that same idea in odds. So in this metric, having parents who are educated looks like it's going to matter more, just numerically, than going to private school. But I really can't compare these two with this one. The odds ratio for GPA is per unit GPA. That's moving from a 2.0 to a 3.0 to a 4.0. That's not the same unit as moving from one group to another. So odds ratios aren't standardized. That's why people, and by people I mean me, don't like them. Say that
I
again?
think it's an easy way to have an inaccurate interpretation.
Is there an easy way to...
I find it's an easy way to have an inaccurate interpretation.
Inaccurate, yeah.
Not standardized.
And I think where the trend came from is that these models are used a lot in medicine, where every predictor is categorical. And that's the way they think of it. Like, here's your possible risk factors. Which one has the biggest impact? What's the biggest odds ratio? That makes sense if your only choices are 0 and 1 in your predictor. But you throw in something continuous like GPA, and then you need to know what unit you're in. Like, you can game an odds ratio. Like, if you divide by 10, your odds ratio is going to be smaller because you changed what a unit is. But the effect should still be the same theoretically. So it's not really standardized. Now, do we have a successful model? Is our prediction of one's choice significantly correlated with their real choice? We would normally answer that in standard linear regression with the model F test, which is a joint hypothesis test for all the slopes. We can do something like that in here, but it disagrees across programs to a problematic extent in this software package. So I'm showing you an alternative way to answer the same question. This is analysis of deviance, is what it's called, resulting from an ANOVA call. Now note, the type is different. For binary, it was like type equals LRT in quotes. For VGLM, it's type equals 1. What does 1 mean? You got to look it up. Good luck.
It's just a code that the
Yep.
software knows.
Yep, it knows what you mean. So I found this in the documentation. So the idea is that we're saying, how tall was the empty model? How tall did the empty model make our data? How tall did the 3 predictor model make our data? And are our data significantly taller in the 3 predictor model? That's what we're answering. Where tallness, height, is log likelihood. So it is printing out -2 times the log likelihood, because that's how we actually do the comparison. It's the difference in heights times -2. So 741 versus 717. Degrees of freedom 3, because that's the number of slopes we have. Deviance, that is the test statistic that we treat as a chi-square. So 24 is the result. There's the corresponding p-value. So on the whole, yes, our model is significantly predictive of this outcome. How predictive? Pseudo R-square. Pick your favorite one. Who cares? That's harder to say. And then I did odds ratios with 95% confidence intervals just to show you what that might look like. So you can get confidence intervals for your odds ratios as well. And if these overlap 1, then they would be not significant, right? These first two are actually odds. The rest of these are odds ratios because these are intercepts. Okay, so do you want to see how to test proportional odds then? How to see if the slope can be shared across submodels or whether each submodel needs a different one. We're going to do that next. Questions before we do that?
So based upon what you just said with the odds ratio, looking at your confidence interval from 0.6 to 1.86, are you saying that then the private would not be significant?
Mm-hmm.
Okay.
If the confidence interval for the logit slope overlaps 0, that means the confidence interval for the odds ratio overlaps 1.
Okay.
Same information.
Double check. Thank you.
Yep. So this helps to quantify the level of uncertainty in this, right? This is all over the place. So it's not a great estimate. All right, so non-proportional odds or partial proportional odds, that's what's up next. Let's play spot the difference. It's my son's favorite game. He gets a magazine sent to our house every week where they have 2 pictures next to each other and there's 5 differences between the 2. That's always the page he goes to first. So let's play spot the difference. What has changed in this equation relative to the previous one? Yeah, lots of subscripts. So now I've got beta 1, and beta 1 comes in 2 different flavors. A beta 1 for the 0 model, a beta 1 for the 1 model. Same with these, same with these. So how many slopes did I have before that we just looked at? 3. How many do I have now? 6. What if I had a 4 category ordinal variable? Then how many do I have? 9. 3 for each. Yeah, what if I have a 5 category? 12.
Can you briefly remind us what the first subscript and the second subscript of the beta are?
Yep. So within this notation system, this is not universal. This is what I'm choosing to notate. The first one is related to which model parameter it is. So beta 0 is my intercept. Beta 1 is the first predictor slope. Beta 2 is the second predictor slope. Beta 3 is the third predictor slope. Then in the second spot, which submodel is that slope going into? The 0 model or the 1 model? And I could have used 1 and 2 to match the R notation, or I could use 0 and 1 to match the stata. I chose the latter because that's consistent with the data, because I start at 0 in terms of my answer scale. So yeah, that's another reason why in practice, people don't often test this, is because the number of slopes grows exponentially with the number of categories that you're testing it across. Now, the genius who wrote Go Logit 2 did you so much of a favor. There's stuff that's built into this that I was really pleased by. So we have gamma as an option. That is a choice for what shows up on your output. And no log suppresses extra information. So that has nothing to do with logs and odds and all that kind of stuff. That has to do with the physical place that the output spits error messages to. So now, let's look at stata output first. LR chi2, that's my likelihood ratio test against the empty model with all 6 slopes. It's significant. Before, we had these 2 neat boxes that corresponded to the 2 submodels directly, and only the intercepts were different. Now, the slopes are different. So for instance, zooming in here, GPA 3 in the first submodel is 0.59. So for every unit GPA, higher GPA, excuse me, the logit of answering 1 or 2 instead of 0 is higher by 0.6. So I'll say that again. For every unit higher GPA, the logit of answering 1 or 2 instead of 0 is higher by 0.6. But then down here, looks like it's a little bit bigger. If I want to predict a 2 instead of a 0 or a 1, then for every unit higher GPA, that logit of a 2 goes up by 0.72. Now these are close. Do you think they're the same or same enough?
Have to
Doesn't
test
matter.
it.
A unit change from like a D and an A?
So it would be like a per letter grade, I think, is a unit in the GPA scale.
I'm saying that with that second model, you get there quicker.
Yeah, you would get there quicker. So these two look meh, like they're close-ish, right? What about the effect of having an educated parent? 1.08 versus 0.99? Yeah, same-ish. What about the effect of going to private school?
Huge difference.
Oh, oops. This one's positive and that one's negative.
Mhm.
So that means the kids whose parents stuck them in private school actually don't want to go to grad school. They've had enough. However, neither of these is significant.
That's great.
So maybe we shouldn't get so excited that they're different in sign because neither one of them is really not different than 0.
Just don't report that p-value.
Yeah, just it's fine. It's fine. Now, the person who wrote this package knew that we were going to answer the question, are these slopes actually different or not? And so they just spit this out. So the option gamma here generates this table that is phrased as one of the slopes as a reference and then differences to get to the other slopes instead. So it directly tests the difference in the slopes across submodels. So beta, it's unfortunately named, I will give you that, is the same thing that we had up here. So beta is, what is the slope in the 0 submodel? Just repeat it. Gamma is now the difference in the slope. So to make it a little more concrete, GPA had a slope of 0.59 in the first submodel. It had a slope of 0.72 in the second. The difference between those is about 0.12 or 0.13, right? That's what this number is right here. So the GPA slope is more positive in the second submodel relative to the first submodel by 0.13. So it's kind of like an interaction term. That's what you can think of these as, is these are like submodel by slope interactions that allow the slope to change across submodels by this much. So I've got a p-value that tells me right here that those slopes aren't different. I could probably lump them together and be fine.
It's a parallel.
Yeah, parallel holds for the effective GPA. Likewise, for grad school, parents went to grad school has a slope of 1.08 in the first submodel. It has a slope of 0.99 in the second. Is my difference going to be positive or negative? Smaller in the second. Yeah, should be negative. So these are signed. The first submodel is the reference. The second submodel is the comparison. So a negative difference means the second submodel's slope was either less positive or more negative. Yes, it's back. 4 kinds are back again. Likewise, private school slope is positive 0.23. Private school slope in the other submodel is negative 0.76. So that's a difference of what I can't do in my head very well, but almost 1.
Mm-hmm.
Oops. Hang on. Nope. I was in the wrong table. My bad. My bad. Scratch that.
No, negative 0.76.
Yep.
77.
Yeah, there we go. So it is going to be negative because it's bringing it from positive down to negative, and the answer is negative. And this p-value, look at this, 0.058.
It's close.
Yeah, this is what people would start using euphemisms for. Like this is approaching significance or trending towards significance or marginally significance or kind of significant.
But it's not.
That it's not. Well, you're supposed to pick your line in the sand ahead of time and not budge from that.
You're trying to be published.
I know. My favorite one is approaching. Because it makes it sound like a cake that's not done yet, and if you just let it cook a little longer, it's going to become significant. It's approaching. Leave it alone. Come back tomorrow. No. And these are the 2 intercepts that we don't need to worry about. So you get a test per slope directly in this table, which is very convenient. However, if I want to test a comparison of the overall models, like as a set, do I need separate slopes or can I have them be together? That's a likelihood ratio test. Is the 6-slope model, does it make the data taller than the 3-slope model? So to do that, I had stored the results of the model in Stata for the previous one. I'm storing the results for this one, and then LR test is a likelihood ratio test. So that is saying, no, the test statistic is 4, probability is non-significant. Looks like the 3-slope model is probably good enough. But this is sort of like Goldilocks and the 3 Little Bears, right? We could have all the same or all different, but Baby Bear wants it in the middle. So what if we customize this? Can we do that? I hope. Yeah, we can. We can do whatever we want, damn it. So I agree that these 2 and these 2 could probably share. But this one, maybe, I'd like to not have that share. So we can tell the software, make the slopes the same for this predictor, let them be different for this other one. We can mix and match. We can customize. Question?
I want to see.
You want to see? Okay. Oh, it gets even better, but we got to go through R first.
Okay.
Whoever made this package did not do you guys a favor. You got to do stuff by hand in R. And by hand, I mean write more code. But parallel equals false is the option that changes this into a non-proportional odds model, different slopes per submodel. And it's grouped differently than in Stata. It goes by term rather than submodel, but it's the same information, same results. It spits out odds ratios for everything still, which is very lovely. I can do a likelihood ratio test to see if the first submodel and the second submodel are different in terms of their height. However, note it doesn't help you. Spot the difference between these 2 lines of output. I dare you. Yep. Nope. Looks like I tested the same model twice. So the technology is not enough to properly tell you what you compared, unfortunately. But here's what you know. Yeah, the proportional odds model versus the non-proportional odds model. So same predictors in both, but the second one has separate slopes across submodels. Yes?
Does that order make a difference?
Yes, it does make a difference. It has to be in the order of fewer. The model that's simpler comes first, because when you do the likelihood comparison, it's fewer minus more.
Thank you.
Yep, it will either yell at you or give you nonsense. I'm not sure which.
Probably nonsense.
Yeah, like what would happen essentially is that your chi-square would be negative, and chi-squares can't be negative. So then it'll be like, I don't know what your p-value is. You have a -4. Good luck with that.
So we always put
Simple model
the proportional odds model first.
Yes, more generally, it is the model with fewer parameters. The simpler model goes first. The more complex model goes second. In R, okay? In R. However, in Stata, it's backwards. In LR test in Stata, it's more and then fewer. Just for fun.
Yeah. Can you do a 3-way model test or no?
Not at the same time.
Thank you.
At least not that I'm aware of. I don't know that I've ever tried it.
I'm not just, that's just a curiosity.
I think we could try it with a third one in here and see what happens.
Cool.
I'll try it. We'll find out. I
Where's-
don't see why you can't theoretically, but the software just might not
Right, yeah,
anticipate
where
it.
she'll get an error.
Yeah, that's what will happen. It'll yell at you, and it'll be an error you can't fix. Yes?
For some models you can. The thing is how to interpret what parameters are being dropped.
Ah,
Because I've done that. I've put 3 models, for example, in multi-level modeling.
mm-hmm.
However, the difference in the parameters is not clear. It doesn't tell you this pair of these results are dropping this and this. No, it's just saying the difference in terms of parameters is 2, 2, 2, 1. There you have your results. So to me it's confusing.
Okay, yep. Thank you for that clarification. So
But you
yes,
can nest models.
it will do more than 2, but then you don't know what you have.
Which is why we do like with like the different, like the lower and the uppers, and we walk across.
Yeah, so like ideally, I'd want to go
Right.
from the simplest to the next and then to the next.
Right.
But it might be skipping the middle one and giving you the endpoints, which would not be helpful.
Yeah.
Okay.
Yeah.
Since it's 313, we're not going to do this yet, but this is the fun part of testing slope differences. I know. Good times. Everyone loves little 0 and 1 columns.
Mm-hmm.
Uh-huh.
But you threw in some negative ones too.
Yes. Yes, I did. Reasons forthcoming. All right. Other questions or comments before we wrap things up on this lovely garbage day?
It is. That's why it's garbage day. I should tell that to Chris.
Happy garbage day?
I don't know where. Yeah. He has issues with which day of the week it is.
Ah, he needs my system.
Like I said, but I don't know where he lives.
Yeah, he's got to figure out his own anchor point. So
right,
yes.
You know, for example, if he lived in the same area, then
Right. All right. Thank you for being here. Let me know if you need anything. Hope to see you Thursday. Bye for now. Bye, Zoomers.